Okay, here we go. So I promised under 30 minutes, and you can go ahead and start your timers. It's definitely going to be under 30 minutes. So alcohol reactivity. As I posted an announcement on, whoops, not quite yet, the diols and phenol chemistry. I'm not going to stress about those. I recommend you read over them. Briefly, a diol is something that just needs two alcohols. So the ways to make those, we would need two reactive sites. So the one the book addresses first is the reduction. So if you had two carbonyls and you reduced both carbonyls, you now have a diol because you'd have two alcohols. The other option, which is a little bit more interesting in my opinion, would be starting with a single alkene. An alkene gives you two reactive sites as well because you have both carbons in that alkene. So if we looked at our carbons, those carbons at either end are our reactive sites. Okay, so when we're thinking diols, it's the standard, is coming from an alkene and reacting it with any one of these reagents to generate the diol. I'm going to ask that you look at least the osmium tetroxide up on your own. The potassium permanganate's a more common reagent. As long as it's cold, it'll do the exact same thing. We're not going to talk about either of those. I'm going to have to say that's the addition chemistry that you need to watch out for. MCPBA is also addition chemistry, but we'll talk about that when we get into chapter 14. But we can use that to generate a diol. And then we'll mention section 13-8 in your textbook refers to synthesizing phenols. We'll talk about that when we deal with aromatic chemistry after the first exam. So we're just kind of simplifying some of the material. The next big thing, I posted an announcement on. On my bike ride home, happened to realize that I completely botched determining the oxidation states for your organic molecules. So I'm going to attempt to do it again, though I do stand by my statement in class that this is really an unnecessary ability or skill. I mean, it works, it's just not super helpful. If we go through and look at each bond having our two electrons, carbon will come in with force. What we're looking at for our oxidation states is how does it change after it's bonded. So what we can do is evaluate the bonds and where the electrons spend most of their times. Hydrogen has a lower electronegativity than carbon, so if we look at carbon's shell, it's really going to take all of those electrons. So we're looking at 4 extra electrons. We're looking at a -4 oxidation state. If we move to the next situation, we would again evaluate all of our bonds with those 2 electrons, but oxygen is more electronegative than our carbon, which means oxygen is going to take those 2 electrons, which really means carbon is only picking up electrons from our hydrogens, and we end up with a -2 charge. So if we look at each hydrogen, collected 1, collected 1, collected 1, lost 1 with the oxygen, there's the plus. Evaluate all those charges, and you get a -2. So this was the part where I messed it up. Okay, so we do look at that total charge or oxidation balance, if you will. Go through and look at our next situation with our hydrogens. Carbon's going to steal the electrons, making those our net negatives. Both oxygens are going to take electrons away from our carbon, so they're going to become positives. The net result is that we have an overall 0 for our oxidation state for the carbon. Okay, so you kind of get the idea on applying the rest of these. I'll let you go through and think about them, except for what I'm pretty sure I'm going to have marked as these hydrogens supposed to be in carbons. We go to this guy, and we evaluate what happens now. Well, if we look at the electrons in our bonds, so first off, 2 bonds with an oxygen, we're going to put that at 2 negatives. Okay, because each of those bonds takes the electrons away from carbon. If we look at the next situation down here, our center carbon is no more or less electronegative than the other one, so those bonds split homolytically. There's no charge balance. It comes out as 0, which means the oxidation state, our oxygens would make our carbon positive. Remember, sorry about that. Like I said, I really don't like this method. Our center carbon comes out as a +2 oxidation state. I do highly recommend that you reference the book, because the book is going to do a much better job of explaining these oxidation states. That said, still don't think it's necessary to actually know it. Okay? So if we go through and look at possible answers, again, you'll notice the one that we just looked at. We make those hydrogens carbons, which is what I'm trying to reference by saying carbon. So it was a typo when I put together the slides. You should see, or should be able to get all of these oxidation states, assuming I put it together right. The second to last one's making me a little bit nervous. If we take a look at that, that one's negative, negative, negative. Carbon is positive, or hydrogen is positive. Yeah. God, I keep doing that. The oxygen takes the electrons, so the oxygen would be negative, leaving the carbon positive, positive, positive. Carbon is more electronegative than the hydrogen, so it takes the electrons from hydrogen. There's our negative, which gives us the +2 oxidation state. Okay. As you can clearly tell, I definitely have problems with it. Again, doesn't matter. I have used this alternate method where we're looking at reduction as an increase in hydrogen atoms and or a decrease in oxygen, whereas oxidation is our increase in oxygen and or a decrease in hydrogen. That definition, I think, is more applicable, and it will get you through probably 90% of the chemistry that you'll see, if not all of it. Where it's more relevant for this section of material is looking at the synthesis of alcohols, and what we're trying to do is start with a carbonyl, and what we're trying to do is get rid of one of those bonds. In the process of doing that, we could then make 2 new bonds, and what we've done is reduced the carbonyl to our alcohol. So the reagents that do that, as we discussed, you've got sodium borohydride, lithium aluminum hydride, and the hydrogen in the presence of platinum. They have different limitations with each. Remember, the sodium borohydride works great. It is selective, though, only for aldehydes and ketones. Meaning, if we go back to our starting material, the atoms at these 2 positions can be carbon or hydrogen, and we'd be fine. If we move to lithium aluminum hydride, it will react with both aldehydes and ketones, but it will also react with esters, so one of those could also be an oxygen. It won't react in a reduction method with carboxylic acids, and that's due to the acidity of your carboxylic acid. Okay, so be aware that the lithium aluminum hydride, being more reactive, reacts with one more carbonyl functional group. The last reagent on this list is hydrogen in the presence of platinum, palladium, or potentially even nickel. It will allow for the reduction of the carbonyl, except it's not selective for just carbonyls. It will reduce all double bonds, all pi bonds. So our hydrogen system goes for pi bonds, not carbonyls. Okay? So in our first 2, carbonyls are our primary targets. So depending on what we want or what's in our structure, we may choose to use different reagents. Typically, we would probably jump for the sodium borohydride in almost all cases because it's a milder reagent. Typically, when we use chemicals, we want to minimize our chemical exposure. So the sodium borohydride is kind of a better choice. Moving on, we can now look at the synthesis of alcohols, and in the process of doing that, what we'll do is we can make them via a grignard. So this is a little bit trickier. With our grignards, what we're saying is we are making an extra carbon-carbon bond. Okay, so let's make that carbon out here. We're going to make that bond. So for that to occur, we have to understand something about the reactivity of our starting materials that would allow this reaction to go forward. So first off, we could evaluate the partial charges in our product. Okay, between the two carbons, our reactive carbons, I'll call them purple and red, do we know anything about either of them? Well, the purple one is bound to an oxygen. It's partially positive, which means for the red one to react, the charge on that red carbon must be partially negative. This is where things get tricky. That means the carbon, the red carbon, is being supplied as what class or chemical reactivity? We're looking at a nucleophile. Okay, which is very odd. We don't expect carbon to have extra electron density, because for it to have extra electron density, it has to have taken it from something that was lower in electronegativity than itself. Very, very, very rare. Okay, which is why we don't see it. Our purple carbon would be supplied as our electrophile. Well, we've conveniently seen a situation where we have an electrophilic carbon. In fact, in the section that we just looked at, we could look at our carbonyl. Carbonyl provides us that electrophilic carbon. So the tricky part is, how do we get our nucleophilic carbon? How can we do that? Well, again, it has to be bound to something that is lower in electronegativity than it. So one option that we've seen already this semester, okay, we could have that carbon bound to a hydrogen. And in most situations, we would say that is not an acidic bond, meaning that hydrogen does not cleave off. We don't typically see C negative and H plus in the presence of a base, right? Okay, what's the exception to that? I guess exception's a poor choice of words. We could see that occur if the hybridization on that carbon was sp hybridized. That changes the electronegativity of the carbon atom enough that we can use a base that will actually deprotonate. The bases that we'd end up having to use, gotta be careful with this one. The base that we would want to use, and I know this is different from what I've said in previous lectures, we want to use sodium amide. Not sodium in ammonia. That will do very slightly different chemistry, very related to our sodium amide, but it again does different chemistry, so you got to be careful with that. The base to remove that hydrogen from an alkyne functional group needs to be sodium amide. Okay, so remember that. So we have this option. We could generate this new carbon-carbon bond using an alkyne. Okay. The next issue with this, or the next thing we'd want to do, is say, well, there are other options, because that really limits our possible functional or functionality. We have to use that triple bond. That's kind of obnoxious. Well, it turns out that we can use a different reagent or a different source of carbon. Okay, and that's really where we come up with this Grignard reagent. What elements have an electronegativity lower than carbon? Hydrogen was a good option, but we also have the potential for using a metal. Metals have extremely low electronegativity. So if I can somehow generate or make a carbon-metal bond, that bond is going to be so weak that the carbon is going to take the electrons away from the metal, and I've got my nucleophile. So this ends up being an extremely reactive species, but it can be generated. It's typically made in situ, meaning it's made in the lab. You'll be making it in lab actually starting on Monday, okay, which will be interesting. So yeah, how do we end up going through and doing that? So making the carbon nucleophile. So Victor Grignard discovered that particular carbon compounds, when they were exposed to, again, particular metals, that the chemistry drastically changed. And this is one of the things that he discovered. When you add magnesium metal, you'll notice that there's 2 electrons with that magnesium. When you added the magnesium metal to an alkyl halide, typically bromide or chloride, but you could probably do it with others, the magnesium would insert itself between the carbon and the halogen. In the process of doing so, that bond is now so polar. So if we take a look at the electrons in that bond between the magnesium and the carbon, carbon is so much more electronegative than the magnesium that the electrons spend most of their time with the carbon. So effectively, when we look at a Grignard reagent, what we have in this case is a negatively charged carbon, and then we'd have our magnesium bromide floating off somewhere else, okay, an ionic bond. This gives us our nucleophilic carbon. This is what can then react with our carbonyls. Okay. Before we get into the reactions with the carbonyls, kind of want to go through a little bit on what's happening with the mechanism of this. Not super important, you wouldn't ever get tested on it, but it's kind of a neat topic to discuss. Okay, so there, yeah, carbon comes nucleophile. Let's evaluate what's going on with our electrons. This is a single electron transfer mechanism, meaning we're looking at radicals forming. The magnesium really doesn't want to have two electrons. Magnesium is a very reactive metal, so it wants to dump them as fast as it can. So what it's going to do is react with the easiest source of electrons possible. Our bromine, or technically our bromide, is the easiest source. So what ends up happening is magnesium shuttles an electron towards the bromine. Bromine says, hey, you know what? Carbon is holding on to its electrons. I bet you I can take the electron from magnesium easier. So it takes its electron that it was sharing with carbon and now shares it with the magnesium. Notice when we draw this mechanism, we're using single-headed arrows to show the flow of one electron. And instead of showing the electrons going from the bond to an atom, or from an atom to a bond, or any one of those things, we're showing both single electrons moving to the space between atoms where our bond is going to form. So it's a slightly different format than we may have seen before. What happens to the other electron that was in that bond? Well, that then goes back to our carbon. Okay, so the result of that is we end up with a radical intermediate. I didn't do a very good job color coding this, did I? Our radical, in this case, aromatic ring. And then we also have a radical magnesium bromide. That magnesium still has an extra electron. Both of these species are reactive because they have unpaired electrons. So in the next step of the reaction, magnesium finds another radical, and we form our magnesium bromide, or our Grignard product. One of the reasons why this mechanism was discovered as feasible was that one of the side products in this case for this reaction was a product known as biphenyl. Biphenyl can really only form in this case through a radical mechanism. Too much sterics and other things get in the way to kind of prevent its reactivity in any other kind of fashion. So the only way we could make this biphenyl is if we had two of these radicals bump up against each other to make the biphenyl. Okay, so we know that it is indeed a radical mechanism. So I want you to see and be aware that this does exist, but you don't need to know this mechanism. You won't be tested on it at any level. So what happens when we take our now newly found carbon nucleophile and we react it with a carbonyl? So in this case, we're starting with a very, very basic carbonyl, effectively as simple as we can get. We have what is known as formaldehyde. Whatever. Okay. When we react the nucleophile with it, our carbon is negative on our Grignard reagent. You'll notice I haven't shown the MgBr, and that's because effectively it's an ionic bond. It's not all that important to include as far as balancing out our reaction. That partial negative is going to react with the biggest positive. Hydrogens may be suspicious as positives, but you must evaluate their bond first. Okay, it's being bound to a carbon. The difference in electronegativity is relatively minimal, which means that hydrogen is not very positive in this case. So what happens instead? Well, we look to our carbon atom. That carbon has two electronegative bonds to an oxygen. Oxygen starts to draw that electron density away. As it does so, the carbon becomes partially positive. That partially positive atom can be stabilized by our negative nucleophile. You'll notice at the end of that reaction, we end up with a negatively charged oxygen. Right? And everything I've said is always, always, always stabilize charge, minimize that charge. Okay? And while we may now have a charge, what we want to do is evaluate, did we actually stabilize the charge in the process? Okay? Well, it turns out, yes, we did. We started with a negative carbon, and now we have a negative oxygen. Which one can hold that negative charge better? The oxygen is more electronegative, can hold that negative charge. We've actually reduced the reactivity in the course of this reaction. So that's a pretty solid feature of our Grignard reaction. The next part of this is that it is again not stable. So we would try and evaluate within the structure, is there something that we can do to stabilize that negative charge on the oxygen? And you'll find that there really isn't anything. We don't have any acidic hydrogens. We have the magnesium bromide floating around, but that didn't do a very good job of stabilizing the carbon. It's still an ionic bond, so we really are just kind of left at a standstill. So the second step with all Grignard reactions is then to react it with H3O+. The reason we add that is the H3O+ gives us an acidic hydrogen, or an H+, that can then stabilize our oxygen. So the electrons from our oxygen now share with the hydrogen. Hydrogen has too many bonds, so we break the polar bond that actually pushes us towards our final product, an alcohol. Okay? So interesting things to note. What type of alcohol did we generate at the end of this? Okay? Vaguely remember the discussion there. We look to see where our oxygen is bound, look at that carbon, and evaluate how many other carbons are attached to it. In this case, only one. We have a primary alcohol. So kind of neat, we can use Grignard reagents to make primary alcohols. Could we use them to make other types of alcohols, say secondary or tertiary? Turns out we can. And we'll do that by going back to our carbonyl starting material, and instead of starting with two hydrogens, as we did in the case of our formaldehyde on either side, we'll have only one hydrogen, and the other position will be a carbon. That carbon now translates through the rest of our product, and when we go to the very end and look and evaluate our product, what happens? Our carbon that has the alcohol attached now has two carbons. We now have a secondary alcohol. Okay? What happens, or is it possible to then do a tertiary alcohol? Well, go back to our starting carbonyl and say, okay, well, instead of having a hydrogen and a carbon, let's just make it all carbons. So the kind of nice part about this is that we can generate a variety of different alcohols using different carbonyl starting materials. So it's something to be aware of when you're trying to put together your carbonyl, or put together your alcohol rather. Make sure you choose a carbonyl that will generate the proper alcohol. Unfortunately, there are some cautions with this. We're generating a carbon nucleophile. Okay? What did we say about a carbon nucleophile? We said it was rather reactive. Why would it be reactive? Why would a negative carbon be particularly reactive? Well, carbon doesn't want to be negative, okay, which is why it's very seldom found in nature, because it's a highly reactive, unstable species, because it will react with virtually anything positive, which is good for our Grignard reactions. It reacts with the carbonyl. So if we look to the product for the reaction shown here, we could draw on our benzene ring, and we'd have, whoa, that was kind of a wicked curl on that. We could then add our extra CH3, and we could then go ahead and put our alcohol on there as well. So what we formed was that new bond, officially here, and actually technically out with that hydrogen as well, where that hydrogen came from our H3O+, and our CH3 came from our Grignard reagent. We can color code some more. So that's kind of nice. We could take advantage of it using it as a nucleophile. But could it act as something else? So what I'm asking there is to think back to those definitions that I said are really, really important. What other species or what other kind of reaction class is there for something that is negatively charged? What you should think of is a Bronsted base. So what happens in the case shown here? Okay, so we would evaluate and say, yes, we absolutely still have that negatively charged carbon. Booyah. What's that negatively charged carbon want to react with? Well, the most positive thing available. We do absolutely have this positive carbon from our carbonyl, but do we have another positive atom? We also have the hydrogen out here. Why is that hydrogen positive? Well, for the same reason the carbon was positive. It's attached to an electronegative element, that oxygen. Okay? Why is that problematic? Well, we now have a competition. We can either have our CH3, our Grignard reagent, act as a nucleophile with our electrophile, or it can act as a base with our acid at the other end. So we have to decide which one is actually going to occur. And a lot of that has to come with how easy or difficult individual reactions are. And as a general rule, acid-base chemistry is much easier than nucleophile electrophile chemistry. Why might that be the case? Think back to general chemistry. What chemistry do you typically do there? Acid-base. Okay, acid-base things happen very, very readily. Why? You're looking at the transfer of a hydrogen ion, relatively small, very simple to kind of shuttle around. Typically, where are your hydrogens found? Outside of a structure. So they're more readily available. We can do that same comparison with this. Our reactive carbon, or our electrophilic carbon, is buried behind an oxygen and two other carbons. Whereas our hydrogen, our acidic hydrogen, is now floating on the outside of the structure, and on one side of it we have the oxygen, which might block, but on the other side there's nothing. Okay, so it's going to be a lot easier to react. So what ends up being the result of this reaction? Okay, unfortunately, it's kind of boring. What we end up seeing as the answer would be this. Well, what's the difference between our answer and our starting material? Ultimately, nothing. Okay, so the main bulk of this that typically trips people up is that we would say effectively no change. And that's not quite fair, because if we said no change, we would also expect to have our CH3 minus present, and we don't. What else is present? In this case, we would form CH4 gas. Okay, our carbon, our negative carbon, would act as the Bronsted base and pick up that hydrogen. We end up with two products. The methane gas would bubble off, and we end up not doing our nucleophilic substitution. So it's one of the big things that you need to be concerned about when you're evaluating Grignard reactions. Is there an acidic hydrogen somewhere in the structure? Okay, if there is, that acidic hydrogen is going to react first, which then means no Grignard reaction in most circumstances. We can get around some of that by being very careful with the reagents we choose and when we choose to use them, which if you encounter those in the textbook, you're more than welcome to take a look at them. If you have questions about it, I would welcome you to ask me questions in class about those kind of rare exceptions on when that can occur. The last thing I'll end you with, make sure, will be reactions, so a little bit of practice here. So if this is the target molecule, we want to come up with the Grignard reagents. Okay, what things could we use to make it? So again, the whole goal of our Grignard reaction is to make the alcohol. So what bonds need to break? Well, if we're going to go backwards, we need to start with that carbon-oxygen double bond. Now the tricky part. Which one of these carbon bonds was made? Okay, kind of a fun question. Which one do you think it was? Red, purple, or blue? Well, in a lab environment, whichever one was cheaper and easier to make. Okay? Any one of those are perfectly valid. And I'm just about to hit the 30-minute mark, so thanks for listening. Talk to you Monday.